Hello, welcome to the experiment on Hooke's law. So essentially we're going to use Hooke's law for a spring in order to determine the spring constant. And Hooke's law in this case we'll use in the objective or the abstract is use the potential energy stored in the spring and balance that against the gravitational force or potential energy due to gravity. And then based on these two opposing forces we can determine the spring constant. And we're going to determine the spring constant using two different methods, and then we're going to compare both those methods by looking at the percent difference between the results of the two methods and see if they are in close agreement. If they are in close agreement, that means that both methods are a good method, or we have confidence that both methods are valid methods to determine the spring constant of a spring. So this is a virtual lab. So what we have here is if you go to the phetcolorado.edu, they have a lot of good simulations on that website. I suggest if you get a chance to take a look at that website and experiment with some of the simulations. But here is basically a spring here. It's an unstretched spring, and here we're going to demonstrate Hooke's law. So the assumptions here for modeling this is that we have an ideal spring. And by an ideal spring, we mean that there is no friction. We neglect friction. And that when we do stretch the spring, we keep it within its elastic region. That is, we do not stretch the spring beyond its elastic region where damage could occur to the spring internally. And then the spring would not return to its normal position when there's no force applied. So one way to check a spring to see that if it's behaving as an ideal spring is if you stretch the spring such, and then if you return it by releasing the force, that it should return to its normal position, as we've shown here. So here, this green vertical dashed green line shows the spring in its unstretched position. That is, no force is applied. Now the spring has potential energy. That is, we can store energy in the spring or in the properties of the metal of the spring, and we can do so by applying a force to the spring. So here in this simulation we have the spring constant at 200 newtons per meter, and then we're going to apply a force. And so let's go ahead and close the pinchers here, and we'll apply a force, and we'll apply up to 100 newtons of force, and I'll release it. Now you can see here the green arrow is the displacement. That is the distance we move the spring from its equilibrium position. That is the displacement. The orange arrow is the force that we applied in order to do that, which is 100 newtons. And since this is static, that is, the spring is not moving, we're holding it in place, that means the sum of the forces must be zero, because there is no net force acting on this point here that would cause the spring to move in either direction. It's just fixed. So that means that the applied force must equal the spring force, which is in the opposite direction. Now notice that the spring force is in the opposite direction where we applied the force to stretch the spring. So what Hooke's law basically says is that the force of the spring equals minus the spring constant K times the distance x the spring is displaced. So in other words, F in the blue here is the spring force. That's basically represents the potential energy stored in the spring. And the x is the displacement here, or the distance the spring moved from its neutral position. So this would be 0 meters. It's a neutral position or unstretched position. So we stretch at a distance x, and the relationship between the force applied in order to stretch that spring is equal to the distance displaced times the spring constant, and the force acts in the negative direction of the displacement. So the displacement vector is positive in this direction, and the force acts in the opposite direction, so it's negative. And that's the basic equation. And so K, we're given K here for the spring constant, and we're set K equals 200 newtons per meter. And that makes sense because if we multiply by units, newtons per meter by displacement, which is in meters, we end up with newtons, which is the force. Newton meter times meter equals newtons, which is the force units of force. So that checks. So that's a simple relationship in this example here. Now the spring constant, this is the spring constant. And again, we assume an ideal spring, which means we neglect friction and we do not stretch the spring beyond its elastic region. The spring constant is really a property or a function of the material of the spring. So the spring constant is really determined by the material properties of the spring itself, and it's something you just have to measure or determine when you design or build a spring. So in this simple example here, for example, we know the spring constant, we know the force applied is 100 newtons, so we could solve for the distance x. So x would just, the magnitude of x would just equal the spring force magnitude divided by the spring constant. So the displacement x magnitude is going to equal the spring force equals the force applied, which is 100 newtons, divided by the spring constant, which is 200 newtons per meter. And if we solve for that, we get that the displacement of the spring is 1/2 meter under these conditions. Now what we're going to do in this experiment is we're going to work backwards. We're going to determine the spring constant. So in this experiment, we're going to find what the spring constant is, K. And this is what we're going to determine. And we're going to do that by stretching the spring by applying its force and get the spring in its equilibrium condition, measure the displacement, x, and measure the force. And then based on that relationship, we can calculate the spring constant K. Now, the way we're going to do this is the force we're going to use the force of gravity, or the weight of a mass. So we're going to turn this whole apparatus here vertically. We're going to hang a spring, and then we're going to apply a mass, M, that has a weight, if you recall, equals mass times gravity. So we're going to take advantage of gravity to be our force, which in this case we're going to replace the applied force with the weight of the mass. And again, the displacement, the force of the spring will counter the force of gravity, and at equilibrium at this distance x, we can measure this distance, and based on that we can calculate the spring constant K. So that's what we're going to do in this experiment. So in the next video, I'll walk you through the technique that we're going to use to determine the spring constant using weights. Thank you, and see you at the next video.